To fly an aircraft in a steady state, climb, cruise or descent, the pilot must apply the stick force necessary to hold the aircraft in the required attitude. In other words, the pilot must hold the aircraft in a state of equilibrium, or trim. The stick force the pilot may need to apply to maintain equilibrium can be quite high, and all human beings find it impossible to maintain a constant stick force for more than a few seconds. Therefore, a means of reducing the stick force to zero is incorporated in all aircraft. This is known as trimming the aircraft. There are several devices used to trim an aircraft. The most common is the trim tab, which is the first trimming device we will look at. You can see the cockpit controls for trimming, plus the tailplane, the elevator and the elevator trim tab. The trim tab is the small red aerofoil mounted on the trailing edge of the blue elevator. The majority of smaller aircraft have an exposed trim wheel in the cockpit, which the pilot can use to move the trim tab. The trim wheel works in a logical way. Move it down by its rear edge to trim the aircraft nose up, as you will see shortly. Some small aircraft and all modern jet transport aircraft have trim switches mounted on the control wheel. The trim switches also work in a logical way. Move them down to trim the aircraft nose up, again, as you will see shortly. All control movements in the following animations are exaggerated for clarity. Let's consider an aircraft with a forward CG, a nose-heavy aircraft. To maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to zero, the pilot must move the trim switches down, or move the rear edge of the trim wheel down. Making this trim input moves the trim tab down, away from neutral with the elevator. As the trim tab moves down, an aerodynamic up force is generated on the elevator trim tab. Eventually, the moment from the trim tab becomes equal to the moment from the elevator. The stick force has been reduced to zero and the aircraft has been trimmed. Please note, when using a trim tab to trim an aircraft with a forward CG position, the cockpit control remains displaced aft from neutral. Your flight instructors will teach you to put and then hold the aircraft in the required attitude using the flying controls. Only after you have achieved equilibrium should you use the trimming devices to reduce the stick force to zero. To fly the aircraft using the trim to change the attitude is bad practice. Let us now have a look at one of the disadvantages of the trim tab: reduced aircraft nose-up pitch authority with a forward CG. Maximum elevator travel is limited by the primary stops. In this example, let's assume the elevator can move 30 degrees up from neutral and 30 degrees down from neutral, a total travel of 60 degrees. 60 degrees total elevator travel will always be available. Let's assume, once again, because of a forward CG, there is a requirement for the pilot to trim the aircraft nose up. You can see that there is reduced aircraft nose-up pitch authority from the elevator with an aircraft trimmed with a forward CG. This reduction in aircraft nose-up pitch authority might make it difficult for the pilot to flare the aircraft for landing. Some trim tabs are not adjustable in flight, but can be adjusted on the ground by maintenance personnel to correct a permanent out-of-trim condition. They are usually only fitted on the ailerons and rudder of light aircraft. When the early jet transport aircraft were being designed in the 1950s, it was found that an elevator trim tab did not provide enough pitch trim authority for the increased speed range and CG range required. So an alternative method of pitch trim had to be used, the variable incidence trimming tailplane. The variable incidence trimming tailplane is still in use on today's jet transport aircraft. You can see that the trim input controls in the cockpit are the same, but now pitch trim is accomplished by changing the incidence of the whole tailplane. As before, for pitch control, an elevator mounted on the trailing edge of the tailplane is still used. For pitch trim, the incidence of the tailplane is changed with the screw jack. The screw jack is mounted inside the rear fuselage and is driven by motors mounted on a gearbox at the base of the screw jack. Once again, we will consider an aircraft with a forward CG, a nose-heavy aircraft. As before, to maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to zero, the pilot must move the trim switches down. Making this trim input drives the screw jack, which in this case decreases the incidence of the tailplane. Please note that while the tailplane is trimming, the elevator is being returned to neutral. The decreased incidence of the tailplane has replaced the downforce from the elevator. The aircraft is still in equilibrium, but with zero stick force. The aircraft has been trimmed. When the trim position is reached, the elevator is faired with the trimming tailplane. The cockpit pitch control has also been returned to its neutral position. Let's now have a look at the advantages of the variable incidence trimming tailplane over the trim tab. The first advantage is that compared to a trim tab, it is much more powerful and has the ability to trim for larger CG and speed ranges. However, there is a drawback associated with the increased power of the variable incidence trimming tailplane. If the tailplane were to change its incidence without being commanded, the pilot could not stop the aircraft from pitching out of control because the elevator is much smaller than the tailplane. This is known as stabilizer trim runaway, and safeguards have to be incorporated in the design to prevent it. Firstly, there is a mechanical brake inside the gearbox which engages and immobilizes the screw jack whenever a trim command from the flight deck is absent. This prevents the airflow from moving the stabilizer. Secondly, there are two switches on the control wheel in the cockpit. The switches are mounted side by side and are easily moved together by the pilot's thumb when required. The switches are wired in series so that if the contacts of one switch do not break the circuit when the pilot releases the switches, the other switch will break the circuit to stop the trim from running. There is also a warning light that illuminates to tell the pilots that the trim is running, and on the Boeing 737, which has exposed trim wheels, their clanking noise when rotating will be an unmistakable warning. If the stabilizer trim does run away, all inputs to the screw jack drive can be removed by emergency shut-off switch action on the flight deck. The second advantage of the variable incidence trimming tailplane is that there is less aerodynamic drag when the aircraft is in trim, a big advantage in the cruise. The third advantage is that trimming does not reduce the effective range of pitch control. As before, the total range of the elevator is limited by the primary stops. But because the elevator is faired with the tailplane when trimmed, both full-up elevator and full-down elevator from neutral is always available to the pilot for pitch control. The only disadvantage of the variable incidence trimming tailplane is that it is heavier than a trim tab and more complex. This disadvantage is far outweighed by its advantages. To maximise aerodynamic efficiency in the cruise, reducing the trim drag to an absolute minimum will significantly increase the distance that can be flown using a given amount of fuel. The illustration shows an aircraft in the cruise with the tailplane trim being used to generate the normal tail down force. As you know, lift must balance the aircraft weight plus any tail down force, so induced drag will be increased. Plus the tail down force is an aerodynamic force, which will further increase induced drag. These together make up the trim drag. We have seen that the variable incidence trimming tailplane gives less trim drag than the trim tab. Now we will consider the benefit from moving the aircraft CG in flight. In this case, we need to move the CG rearwards. This is done by pumping fuel from the wing tanks to a trim tank at the rear of the aeroplane, usually fitted inside the fin or the tailplane. Pumping the fuel to move the CG is an automatic function and in practice is a slow and almost continuous operation. But as usual, we have exaggerated the illustration for clarity. Please note that the trim switches are not being used, but the tailplane is changing incidence to maintain equilibrium as the fuel is being transferred from the wing to the tail, another automatic function. With power flying controls, there is no feedback of aerodynamic forces to the cockpit controls. The stick forces are generated by the artificial feel system. Therefore, when the aircraft is being trimmed, the trim system will have an input to the artificial feel system that reduces the stick forces as appropriate. We have now reached the end of our study of flying controls. Please feel free to review the lessons as many times as you like, because they contain a lot of detail in which the examiners are interested.